Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss surface condensers and the condensing steam turbine. More of the world's energy is consumed in surface condensers than for any other single use. Even at the very start of the Industrial Revolution, the father of the surface condenser, the barometric condenser, consumed huge amounts of heat. The central idea of our industrialized society is to have machines do the work formerly done by humans or animals. The technical problem that kicked off the Industrial Revolution was flooding in the tin mines of Cornwall, a region in southern Britain. To work the mines and extract the valuable tin ore, steam-driven reciprocating pumps had been constructed. These plunger-type pumps were moved up and down by the famous beam engines, and these reciprocating engines were powered by steam, thanks to the efforts of Thomas Newcomen in 1712. The motive steam for these reciprocating engines was charged into a steam cylinder. The piston inside the cylinder was pushed up by the expanding steam. The piston then lifted the beam attached to the reciprocating pump. Cold water was admitted next and jetted into the steam cylinder. The cold water absorbed the latent heat content of the steam. The steam pressure inside the cylinder dropped, and the piston dropped. This pulled the beam down. It was the up and down movement of the beam that powered the reciprocating pump. The structures, beams, foundations, and bits and pieces of ancient machinery are scattered all across Cornwall. If you choose to explore the mining areas of Cornwall, be very careful as many of these shafts are hundreds of feet deep. There are numerous stories about people and livestock slipping into these disused shafts and being drowned in the accumulated water or simply falling to their deaths down the mine shafts. There was a big problem with the initial beam engine design. When the cold water was admitted into the steam cylinder, the water not only absorbed the latent heat of the condensing steam but also cooled the iron walls of the steam cylinder. Then when the next charge of steam was admitted to the cylinder from the boiler, a lot of the steam's heat was wasted in reheating the iron walls of the cylinder. Then again, an awful lot of cold water was wasted in cooling the metal of the steam cylinder each time the motive steam had to be condensed. All this wasted a tremendous amount of coal. Actually, only 1 to 2% of the energy of the coal was converted into useful work. Quite suddenly, the steam engine was revolutionized. Its efficiency was increased by a factor of 10. This was all due to the innovations of James Watt, who invented the external barometric condenser in the late 1760s. The second law of thermodynamics. Steam power was fully developed before the introduction of the science of thermodynamics. The steam engine was designed and built by ordinary working people, such as Mr. Newcomen and Mr. Watt. Mr. Watt's invention is illustrated in picture. Rather than cooling and condensing the steam in the cylinder, the steam was exhausted to an external condenser. In this external condenser, the exhaust steam was efficiently contacted with the cold water. This external or barometric condenser rather looks and performs like the deaerator we discussed in deaerator's video. The external condenser obviously achieved Mr. Watt's original objective. He could condense the steam without cooling the cylinder. But the barometric external condenser was found to have an even more important attribute. Let me explain. The boilers in those days were not pressure vessels. They were constructed from sheets of wrought iron and assembled by riveting and hammering the seams. At best, they could hold a few atmospheres of steam pressure. The low-pressure steam generated did not really push the beam and piston up. The beam was pulled up by a heavy weight attached to the far end of the beam. This also pulled the piston up. Well, if the steam did not really push the piston up, what did the steam do? Answer is, the condensing steam pulled the piston back down. As the steam condensed, it created an area of very low pressure below the piston as shown in picture. This low pressure sucked the piston down. The colder the temperature at which the steam condensed, the lower the pressure at which the steam condensed. The lower the pressure in the steam cylinder, the more forcefully the piston was drawn down. And the more forcefully the piston was sucked down, the more work the beam engine could do with the same amount of coal consumed. It is easy to see how the barometric condenser could condense the exhaust steam more efficiently than periodically squirting water into the steam cylinder. The barometric condensers could absorb the latent heat of condensation of the steam at temperatures of 120 degrees Fahrenheit or less. Water condenses at a pressure of 25 inches mercury at this temperature. This extremely low vacuum sucked the piston down more forcefully because of the greater differential pressure across the cylinder. In other words, on top of the cylinder, there was atmospheric pressure; below the cylinder, there was the pressure in the barometric condenser. Two problems arose with the use of the barometric condenser. First, if the condenser operated at subatmospheric pressure, how can the water be drained out of the condenser? That is easy. Set the condenser on a hill 34 feet high. Then drain the water down through a barometric leg to a seal pot. The pressure that a column of water 34 feet high exerts is equal to 1 atmosphere, or 1 bar. Hence the term barometric leg. The second problem was air leaks. Air drawn into the system would build up in the condenser. This non-condensable vapor was drawn off by using a steam jet. Certainly, if we could generate steam at a higher pressure and temperature in the boiler, we could push the piston shown in picture up with greater force. Thus thought Richard Trevithick of Cornwall, who pioneered the use of high-pressure steam in the 1790s. And as the mechanical design of boilers has improved over the last 200 years, this has been done, and we certainly can now push up the beam with greater force. As a result, the amount of work that may be extracted from steam has more than doubled. But it was James Watt, working alone, repairing a model of a Newcomen engine, one who made the big leap forward in improving the efficiency of the steam engine. And what, dear gentlemen, does all this have to do with the second law of thermodynamics? This law states W equals delta H times T2 T1, where W equals amount of work that can be extracted from a mode of steam. Delta H equals enthalpy of the mode of steam minus the enthalpy of the condensed water. T2 equals temperature at which the steam is generated in the boiler. T1 equals temperature at which the steam is condensed in the barometric condenser. According, then, to the second law of thermodynamics, Mr. Watt lowered T1. But, of course, the professors who worked out these laws were just formalizing the discoveries that practical working people had made 100 years before their time, using common sense and craftsmanship. The surface condenser. There is another problem with the barometric condenser that did not become apparent at first. When the British Navy decided to convert from sail to steam, this problem was immediately obvious. While steam can be generated from seawater, it is far better to use fresh water, especially if one wishes to generate high-temperature, high-pressure steam. And as freshwater supplies are limited at sea, it would be great if the condensed steam could be recycled to the boilers. But the cooling water supply to the barometric condensers was naturally seawater, which mixed with the steam condensate. The solution is straightforward. Do not condense the steam by direct contact with cold water, as is done in the barometric condenser. Condense the steam by indirect contact with the cold surface of the tubes in a shell end tube condenser. Hence the name surface condenser, a sketch of which is shown in picture. Compare this picture with the surface condenser. Is there really much difference? Other than recovering clean steam condensate for reuse, there is no difference at all. I last used a barometric condenser on a sulfuric acid plant reactor feed gas boost blower, and it worked just fine. Using the second law of thermodynamics. The mode of steam supply to a condensing steam turbine such as that shown in picture is 360 degrees Fahrenheit and 150 psig saturated steam. The turbine is exhausting to a surface condenser. The cooling water to the condenser is 92 degrees Fahrenheit. The turbine is driving a centrifugal compressor. The calculated horsepower produced by the turbine is 10,000 brake horsepower. Your supervisor has told you that colder 62 degrees Fahrenheit well water is to be substituted for the 92 degrees Fahrenheit cooling tower water. Supervisor has given you the following additional information. The steam jets are oversized for the non-condensable flow, which consists of only a very few pounds of air in leakage. The motive steam flow to the turbine is not known but won't change. The pressure in the surface condenser is unknown and cannot be measured. The cooling water flow rate is not known but will not change either. The water will just be colder. The efficiency of the turbine and compressor is not known but is presumed to remain constant. Supervisor has asked you to calculate the new compression horsepower output from the compressor. Using thermodynamic equation, we note compression work W is proportional to horsepower. Delta H will go up from its prior value a little because the enthalpy of the condensed steam will be lower, because it's colder. As the cooling water supply is 30 degrees Fahrenheit lower, we will assume that the condensation temperature T1 in thermodynamic equation is reduced by 30 degrees Fahrenheit. The enthalpy difference between 150 psig saturated steam at 360 degrees Fahrenheit and steam condensed under a good vacuum is roughly 1000 BTU per pound. The enthalpy reduction of condensing the steam at a 30 degrees Fahrenheit lower temperature will increase delta H by 30 BTU per pound. Delta H in thermodynamic equation thus increases by 3%. T2, the temperature of the motive steam, is always 360 degrees Fahrenheit. With 92 degrees Fahrenheit cooling water, we will assume that T1 is 120 degrees Fahrenheit. T2 minus T1, with 92 degrees Fahrenheit cooling water, is 360 degrees Fahrenheit minus 120 degrees Fahrenheit, equals 240 degrees Fahrenheit. T1, with 62 degrees Fahrenheit cooling water, is 30 degrees Fahrenheit cooler than T1, with 92 degrees Fahrenheit cooling water. That is, the new T1 is 120 degrees Fahrenheit minus 30 degrees Fahrenheit, equals 90 degrees Fahrenheit. T2 minus T1, with 62 degrees Fahrenheit cooling water, is then 360 degrees Fahrenheit minus 90 degrees Fahrenheit, equals 270 degrees Fahrenheit. With the cooler well water substituted for the warmer cooling tower water, T2 minus T1 has increased by 270 degrees Fahrenheit minus 240 degrees Fahrenheit, divided by 240 F, equals 12.5%. Combining the delta H effect of 3% with the larger T2-T1 effect of 12.5% in thermodynamic equation results in a compression horsepower increase of 16% or about 11,600 brake horsepower total. If you wish, work through the same problem but use 5 psig saturated steam, which was used to power steam engines in the 18th century, rather than the 150 psig saturated steam we used in our current example. The answer will illustrate why Mr. Watt is still well remembered, especially in Cornwall, along with justly revered Mr. Trevithick. Imagine you are sitting in a meeting when the vice president asks, should we use an aerial cooler or colder seawater to condense the power plant turbine exhaust steam? The chief engineer offers to run through the relative efficiency of the turbine for the two cases using his computer model and report back after lunch. You, the junior staff engineer, look up into space and after a few moments state, based on the second law of thermodynamics, I've calculated an enhanced efficiency of 16.1% for the cooler seawater case. I always add that extra decimal for dramatic effect. Surface condenser problems. In my lecture on steam turbines, we reviewed several problems pertaining to steam jet-free condenser and intercondenser problems. The surface condensers, which serve condensing steam turbines, are subject to all the same problems and a lot more. A standard surface condenser package with an associated two-stage jet system is shown in picture. By way of summarizing many of the problems that occur with this sort of equipment, I will relate one engineer trials and tribulations with K805, an auxiliary combustion air blower at the refinery. The problem with this new air blower was that they could not bring the turbine speed above its natural harmonic critical speed. The critical speed of a turbine is stamped on the manufacturer's nameplate. Turbines are typically run well above their critical speed. If, for some reason, a turbine is run close to its critical speed, it will experience uncontrolled vibrations and self-destruct. For a surface condenser to work properly, non-condensable vapors must be sucked out of the shell side. This is done with a two-stage jet system, as shown in picture. When he first commissioned the jets, they were unable to pull a good vacuum. Moreover, water periodically blew out of the atmospheric vent. He found, after considerable investigation, that the condensate drain line from the final condenser was plugged. He directed the maintenance crew to disassemble and clean the drain lines from both the final condenser, B, and the primary jet discharge condenser, A. Unfortunately, they failed to reassemble the loop seal from condenser A. But what is the purpose of this loop seal? The pressure in condenser A is greater than that in the surface condenser and less than that in the final condenser, condenser B. This means that condenser A is operating at vacuum conditions. This prevents the condensed steam formed in condenser A from draining out to atmospheric pressure, unless the condenser is elevated by 10 to 15 feet. To avoid this problem, the condensate is drained back to the lower pressure surface condenser. To prevent blowing the non-condensable vapors back to the surface condenser as well, a loop seal is required. The height of this loop seal must be greater than the difference in pressure, expressed in feet of water, between the surface condenser and the primary jet discharge condenser, condenser A. With the loop seal gone, the non-condensable vapors simply circulate around and around through the primary jet, but no substantial vacuum in the surface condenser can be developed. Having replaced the loop seal piping, some units use a steam trap instead of this loop seal. He started steam flow to the turbine. But the vacuum in the surface condenser, which had started out at an excellent 27 inches mercury, slipped down to 14 inches mercury. This loss in vacuum increased the back pressure in the turbine case. The higher pressure in the turbine case reduced the velocity of the steam striking the buckets on the turbine wheel, which reduced the amount of work that could be extracted from each pound of steam. Note that the vacuum measurements of 27 inches mercury and 14 inches mercury are expressed in the vacuum measurement system typically used in refineries where 30 inches mercury equals 0 millimeters of mercury, that is, full vacuum. 0 inches mercury equals atmospheric pressure, that is, no vacuum. Thus 27 inch of mercury vacuum is really 3 inches of mercury absolute. And 14 inches of mercury vacuum is really 16 inches of mercury absolute. I know this is confusing, but that's the way vacuum pressure measurements and gauges are in process plants. For practice, pull out your Mollier diagram. If the motive steam is 400 psig and 650 degrees Fahrenheit, what is the effect of reducing the vacuum in the surface condenser from 27 to 14 inches mercury? Answer is 13% loss in horsepower. The turbine began to slow. It slowed to its critical speed and began to vibrate. Before shutting down the turbine to avoid damage due to the vibrations, he noted the following. The temperature of the turbine vapor exhaust to the primary jet had increased from 125 to 175 degrees Fahrenheit. The temperature of the condensate draining from the surface condenser had decreased from 125 to 100 degrees Fahrenheit. The condensate pump was cavitating, as indicated by an erratically low discharge pressure. The increase in the vapor outlet temperature from a condenser, as compared to a decrease in the temperature of the condensate from the same condenser, is a sure sign of condensate backup. The condensate is covering some of the tubes in the surface condenser. This subcools the condensate and does no harm. However, the number of tubes exposed to the condensing steam is also reduced. This forces the steam to condense at a higher temperature. In effect, the condensate backup has reduced the surface area of the condenser available to condense the steam. The higher the condensation temperature of the steam, the higher the condensation pressure of the steam. Just like the deaerator. Take a look at picture. It is the vapor outlet temperature of the surface condenser, rather than the condensate outlet temperature of the surface condenser, that determines the real condensing temperature and pressure of the exhaust steam. Condensate pumps serving surface condensers have a common problem. Their suction is under a vacuum. For example, let's assume the following for picture. The surface condenser pressure equals 27 inches mercury. The condensate water level in the boot is 11 feet above the suction of the pump. 1 inch of mercury, 1 inch mercury, is equal to a head of water of 1.1 feet. This is a good rule of thumb worth remembering. The pressure at the suction of the condensate pump is then 27 inches mercury minus 11 feet H2O times 1 inch mercury divided by 1.1 feet H2O equals 17 inches mercury. Often, centrifugal pumps develop seal leaks. If the suction of a centrifugal pump is under a vacuum, air will be drawn into the pump through the leaking seal. The pump's capacity will be severely reduced. To stop the suspected air leak, he sprayed water from a hose over the pump's seal. Now, instead of sucking air, the leaking seal drew in cold water. As a result, 1. The cavitation of the condensate pump stopped. 2. The high water level in the boot was pulled down. 3. The condensate outlet temperature increased. 4. The vapor, or non-condensable, outlet temperature decreased. 5. The vacuum in the surface condenser was restored. 6. And the turbine speed came back up, well above its critical speed. But not for long. After 15 minutes of operation, the turbine speed slipped back down. Once again, he had lost a lot of vacuum in the surface condenser. Once again, the vapor outlet temperature had dramatically increased. But this time, the condensate outlet temperature had also increased. What was his new problem? He now observed that the surface condenser cooling water outlet temperature had increased from 100 to 135 degrees Fahrenheit. This is a sign of loss of cooling water flow. As none of the other water coolers in the plant had been affected, he concluded that the cooling water inlet to his surface condenser was partly plugged. He had the front end plate on the cooling water side of the surface condenser, called the channel head cover, removed. Most of the tube inlets in the channel head tube sheet were plugged with crayfish. The offending wildlife were removed. The condenser was reassembled. The motive steam was started to the turbine. Both the turbine and the air blower were running well above critical speed. They lined the flow of combustion air up to the combustion chamber. Everything was finally going his way, except for one minor problem. The governor speed control valve, shown in picture, was 100% open. The plant's boiler house was not sending us the proper pressure steam. He was supposed to be getting 460 psig steam, but was only receiving 400 psig steam. This reduced the steam flow through the nozzles in the turbine steam chest by 15%. The operators at the power station assured me that the problem was temporary. The normal 460 psig steam pressure would be restored by morning. Ladies and gentlemen, it is not a good idea to run a turbine with the governor speed control valve wide open. Why? Because you no longer have any speed control. And the turbine speed is then free to wander. The rest of this story is pure philosophy. During the evening, operators decided to increase the combustion airflow from the blower or air compressor. This is done by opening the suction valve to the blower. Naturally, it requires more work to compress more air. But the turbine could not produce any more work or horsepower because the steam turbine's governor speed control valve was already 100% open. So, the turbine slowed down. And what was the only possible speed that it could slow down to? Why, the critical speed, of course. The turbine and blower began to vibrate. The bearings were damaged. The turbine's rotor became unbalanced. A rotating element on the air blower touched a stationary component in the blower's case. The stationary component broke off and wrecked the blower. That was the end of K805. By what law of nature was the turbine forced to slow exactly to its critical speed? You see, dear gentlemen, life is perverse. And if anything bad can happen, it is going to happen to anyone. Non-condensable load. The gas that accumulates inside the surface condenser is called the non-condensable load to the steam jets. Some of the non-condensable load consists of CO2 accidentally produced when the boiler feed water is vaporized into steam. Air leaks through piping flanges and valves are other sources of non-condensable vapors. But the largest source of non-condensable vapors is often air drawn into the turbine case through the shaft's mechanical seals. To minimize this source of leaks, 2 or 3 psig of steam pressure is ordinarily maintained around the seals. However, as the turbine shaft seals deteriorate, air in leakage problems can overwhelm the jet capacity. This will cause a loss of vacuum in the surface condenser. If vacuum in the surface condenser is bad, there are 2 possible causes. Either the jets are at fault, or the surface condenser is at fault. Air leaking into the surface condenser results in vapor binding. This causes an increase in the shell-side heat transfer thermal resistance. In effect, the steam does not make good contact with the exterior of the surface condenser tubes. This vapor binding effect often appears to the operators as if the tubes are fouled with cooling water deposits. Thus, even without any loss in vacuum due to an air leak, the performance of a surface condenser is degraded as a consequence of an increasing concentration of air or non-condensable inside the surface condenser. Whereas shell-side fouling in a surface condenser is uncommon, loss of heat transfer coefficient due to air binding is as common as tube-side fouling due to poor quality cooling water. Jet problems. These include too high or too low motive steam pressure, excess wear on the steam nozzles, high condenser back pressure, and air leaks that exceed the jet's capacity. To determine whether a poor vacuum in a surface condenser is due to such jet problems, consult the chart shown in picture. Measure the surface condenser vapor outlet temperature and pressure. Plot the point on the chart. If this point is somewhat below the curve, your surface condenser's loss of vacuum is due, at least in part, to jet deficiencies. Surface condenser problems. These include undersized surface condenser area, waterside fouling, lack of water flow, condensate backup, leaking seal strips around the air baffle, and excessive cooling water inlet temperature. To determine whether a poor vacuum in a surface condenser is due to such heat transfer problems, plot the surface condenser vapor outlet temperature versus pressure on the chart shown in picture. If this point is on or slightly below the curve, it is poor heat transfer in the surface condenser itself that is hurting the vacuum. The curve in picture also represents the best possible vacuum that can be obtained in any surface condenser. The majority of surface condensers I have seen do operate right on the curve. Condensers operating below the curve are typically suffering from air in leakage through the turbine shaft seals. Refinery vacuum precondenser fouling. A precondenser in a refinery vacuum tower service is like any surface condenser, with the following characteristics. Triangular tube pitch. 3/4 inch tubes. 15/16 inch tube spacing. Fixed tube sheet. The fixed tube sheet configuration means that the bundle cannot be extracted from the shell. The small tube pitch configuration makes it utterly impossible to chemically clean the shell side in place for any shell ID much above 30 inches. Recently, someone had a refinery precondenser that had a 25 mm of mercury delta P. Service provider tried the following chemical cleaning procedure. Step 1. Steam through with an aggressive vapor phase solvent used to clean tower internals. Step 2. Circulate methanol for several hours and flush with water. Step 3. Circulate toluene for several hours and flush with water. Step 4. Circulate HCl for several hours and flush with water. Step 5. Steam through. Afterward, delta P had dropped from 25 to 20 mm of mercury. Calculated clean delta P was 5 mm of mercury. Cost of the cleaning was $130,000. The client was not pleased with this result. The correct design, then, for this service is pull-through bundle that can be extracted from the shelf for cleaning. 1-inch outer diameter tubes. Rotated square pitch. 1.5 inches tube spacing. A 3/4 inch tube on 1.25 inch spacing, I would imagine, is also cleanable. A fixed tube sheet exchanger in a refinery pre-condenser service for a vacuum tower is a throwaway item. One operator just engaged in this exercise. Replacement for the 60 inches ID shell, as per specs above, was $1,300,000 in 2013. Not a happy situation. Function of the final condenser. We discussed before that the drain from the final condenser shown in picture had plugged. Rather than unplugging the drain, could we have simply disconnected the final condenser, condenser B, and vented the discharge from the secondary jet, jet 2, to the atmosphere? Would this have helped or hurt the vacuum in the surface condenser? The final condenser hurts the upstream vacuum. The final condenser increases the discharge pressure from the secondary jet and thus makes the jet system work slightly harder to expel the non-condensable gas load. What, then, is the true function of the final condenser? Well, if the tiny amount of condensed steam is not needed, the final condenser serves no function at all. It may safely be discarded. Why, then, do surface condensers come with final condensers? It is just a convention that, for most plants, makes no particular sense. It is really just a holdover from the design to conserve freshwater on the old British naval steamships. Leaking ejector condenser partition plate. On the vapor outlet of steam turbine surface condensers, there is a 2-stage ejector system and a 2-stage condenser. Referring to picture, this 2-stage condenser is actually a small condenser divided into 2 portions on the shell side by a partition baffle. What will be the consequences of a leak developing in this partition baffle? Someone just encountered this problem last week for the first time, although he now understands that it is not uncommon. For clarity, let's assume for picture that valve A is closed, and valves B and C are open. Note that the inlet pressure to the second stage jet, 380 millimeters of mercury, is double its design pressure. Hence the pore vacuum, 100 millimeters of mercury, in the upstream surface condenser. If a leak develops in the partition plate in the ejector condensers, then non-condensables, that is, air, will leak back from the 780 millimeters of mercury discharge of the second stage jet into the 380 millimeters of mercury suction of the second stage jet. This internal non-condensable leakage will cause internal recirculation and overloading of the second stage jet. Hence the pore performance, that is, only a 780 divided by 380 is equal to 2.05 compression ratio of the second stage jet. The symptoms of this problem were: closing valve C improved the surface condenser vacuum by 30 millimeters of mercury. Closing valve C did not cause water to blow out of the atmospheric vent. With valve C open, the atmospheric vent was under a slight negative pressure. With valve C shut, the atmospheric vent began to blow out non-condensables, air, in an erratic manner. The solution to this problem was not to repair the defective ejector condenser. This had been done before, but without preventing a repeat failure. As I've explained in lecture, the final or second stage condenser serves no function. It's a design error. So, in this case, as shown in picture, valves B and C were shut and the local atmospheric vent valve A was opened. This allowed the second stage jet to discharge directly to the atmosphere. As a result, the pressure in the surface condenser dropped by about 1/2. In reality, valve A did not exist. The second stage jet was vented to the atmosphere by disconnecting the piping at the outlet flange of the ejector. Surface condenser heat transfer coefficients. Heat transfer coefficients in my lectures have the units of BTU per hour square feet degree F, where the square feet term refers to the surface area of the surface condenser. The degree F term refers to the condensing steam temperature minus the average tube-side cooling water temperature. Most unfortunately, an incorrect correlation for heat transfer coefficients for surface condensers has become widely disseminated in several books devoted to heat transfer. This correlation predicts heat transfer coefficients for clean condensers of about 650, when the waterside velocity is about 6 feet per second. Use of this correlation has led to some extremely serious problems. The correct heat transfer coefficient for a clean surface condenser, with a waterside velocity of 6 feet per second, is about 200 to 240. Including an allowance for fouling, we suggest you use 140 to 160 overall heat transfer coefficients for steam surface condensers. While I have observed clean coefficients approaching 400, I would not count on maintaining 400 after several years of service on an industrial surface condenser. Effective air on condensate. Film heat transfer. I've been helping a young engineer working at a plant with a steam surface condenser problem. Actually, this young engineer is very smart. Smart enough not to follow my advice. For over a year I've been telling him that the cause of his poor surface condenser performance was a low heat transfer coefficient due to fouling on the condenser shell side. This turned out to be 100% correct. The poor heat transfer in the shell side of the surface condenser was increasing condenser vapor outlet temperatures, and hence the vapor pressure of water in the condenser outlet. Also correct. The high water vapor pressure was thus limiting vacuum. Correct. Therefore, I concluded that the shell side of the condenser must be fouled with hardness deposits from the poor quality motive steam to the turbine. Thus, the shell side needs to be chemically clean. 100% wrong. Recently, the condenser heat transfer coefficient was doubled just by improving the performance of the first stage ejector. This was done by improving condensate drainage from the lead interstate condenser on the discharge of the first stage ejector. As the amount of non-condensables, that is, air, plus steam flow from the surface condenser was increased, the interface resistance between the cooling water tubes and the condensing steam was greatly reduced. This doubled the observed overall heat transfer coefficient in the surface condenser. A vast increase, 5 inches mercury or 126 millimeters of mercury, in condenser performance was achieved. This has nothing to do with the effect on the partial pressure of water due to air leaks. It is really fouling of the exterior of the tubes with air. I know this is complex, but it is all explained and quantified in the literature. This problem is best described by the term vapor binding. To restore drainage from the lead interstage condenser, the engineer flushed out the drain line, which was full of black gunk. The literature reference is Henderson and Marcello, 1969, Film Condensation in the Presence of Non-Condensables, Journal of Heat Transfer, Volume 91, August, pages 447 to 450. Also, I have a message for Mrs. Henderson and Marcello. God sees the truth, but waits. As for the young engineer, the hero of the story, he's still waiting for his reward from the owners of that plant. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.